So then you have like statements, right? These P statements, we can combine those. So we have a negative 0.125 and a plus 0.866 P. So when those get combined, looks like it is 0.741 P. And then these can get combined, the minus 50 and the 21. They're both minus. So that's going to be a minus 71.65 equals 0. Why my cord is doing that? Stay. And then how do we solve this? Move this to the other side and divide by the 0.741. So P equals 96.69. £96.69 to push on this thing to get it right before it moves. That's a lot of load for a 100-pound block. The bunch of friction. Yeah, it's because you're not pushing at a very efficient angle, right? You're not pushing up the hill, you're pushing kind of into the hill. So not cool. So the answer, the true answer is P would equal anything greater than 96.69. Yeah, it's actually not equal to. To get it to move, it would have to be greater than 96.69. Because 96.69 is still static. It's the maximum you could push and it wouldn't move actually. So anything greater than that, and it goes. So that's a little tricky, right? Simultaneous equations. You have to be super careful with your algebra. So the number you come up with is what we call impending motion, meaning that's right before it moves. So if they want to know how much load to get it to move, it's got to be greater than this. Any like 96.70 and it moves.
If it's exactly 96.69, it's not going to move.
Right.
It's just a little bit over, isn't it?
Yep, that's exactly right. It's called impending motion. Yep. So our whole concept here is we keep it static, but we go right to the limit. So then we know, okay, anything over that value and it goes. There is another way to work it. I don't know if it's simpler or harder, depending on how you like algebra and how you like this, right? How comfortable that is. That's not very comfortable. There is another forced triangle method that I'll talk about in a second. Maybe we'll do the next problem that way. Because we got another one, number 8. 8 says, compute the horizontal force P required to prevent the block from sliding down the plane. 175-pound block, P at a bad angle again. Coefficient of friction of 0.65, so it's pretty sticky. .65, yeah. So this time, we're trying to just hold it in place, right? So that means friction is going up the hill because motion would be down the hill if it actually goes.
Degrees.
25 degrees is the slope, yeah. All right, I think we'll do this one by the equation method again, just because it's good practice. kind of what we just did. And then I'll show you the triangle method. So that means this is 25. It's kind of the first thing I do is set the axis up and then get the angles for the forces. Right, so our axis is going to be here again, the XX axis, the Y axis. This angle is always going to be the same as the slope, 25 degrees. And then I put my components in and try and get their directions. So remember, the components are going to go together tip to tail. So they got to go together tip to tail and then end at the tip of the hypotenuse. So once you get all those in, then you can just apply your equations again. Some forces in the X. And we're going to put it in terms of P and in terms of N. That's going to be our target again. Same thing. So you write the equation first, then I'll write the equation. We can check each other. And I'll give you a second to do that.
What's the S in the?
Static. Oh, in the force equation?
It's F equals mu times S.
Oh, this equation. Friction equals the static coefficient. S for static, because there is a kinetic coefficient. So once something starts to slide, the friction goes down. If you've ever slid anything, a box or a table or a fridge, anything, to get it to move takes more load. Once it's moving, it takes less load to keep it moving. So this stands for static, Ben, coefficient. So I use sine for the 175 because it is opposite of the angle. And it's going downhill, so that's negative. And then cosine of the 25 here, because it's adjacent to the angle. And it's going uphill. So it's positive. And then F we want to pull out. And we want to put in mu SN or 0.65 N. Yep. So that gives us our two terms, N and P. So now I can go after the next equation. Forces in the Y plus N minus cosine 25 times 175, and then minus sine . So I'll solve this bottom equation for N. And then I'll also get rid of these and put numbers in. Oh, I can do that whole number. 158.604. This is just a number. That's just a number. 423. Wouldn't it be the opposite? Oh, yeah. Thank you. Yeah, absolutely. Sign would change. Excellent catch. So that's our end statement. Since we got it from this equation, we substitute it back into the other equation. So that's going to be plus 0.65. I'll write it all the way out. You wouldn't necessarily have to. You could just go for some of the simplification. I'll turn this into a number. 25. Sine 75. $906. It's complicated. You just got to go through it really kind of carefully and slowly. So. And really be careful with your signs. So these. Once we got the two P statements, I just combine those. End up with 1.181 P. And then these two, we just move to the other side and add them because they're just numbers. We ended up with a minus 29,134, and then you do the division, you end up with a minus 24.66. So why the minus? What's the minus mean when we get a negative when we solve statics problems? That's right. That's exactly right. So they want impending motion down the hill, right? So that means, yeah, that means that actually to get to impending motion down the hill, we have to pull on it, not push on it. The assumption was push because that's the arrow we started with, but that's not true. It's not much slope, 25 degrees, and it's got a lot of friction, 0.65. So to get to impending motion, we literally have to pull it down the hill, 24.66. To get it to move, anything more than 24.66. Oh, not equals. P greater than 24.66, and I can make it positive now because I went and turned the arrow around on P. So saying that's the same rules we had before. If you solve for a variable in a statics problem and it comes up negative, you have the direction wrong. So this just means we assumed we had to like hold it in place, you know, or it would slide down the hill. That's not true. Like you just let go of it. It's not moving. To get it to move, we have to pull on it. 24.66 pounds. Tricky. Tricky. All right. We're going to take a short break and then I'm going to show you the triangle method on that problem. So I don't know, 5, 10 minutes, pause recording. All right. So the next method is called the angle of repose method. So what we have to understand is we have to understand, like in a statics problem, if you have a block on a surface, that block is going to slide at some point as the angle gets great enough. Okay. So what we have to understand is the weight always acts vertically downward, right? So as the slope changes, see if I can do this. And I'm going to use, there's two sides to these blocks. There's a sandpaper side and then a smooth side. They should slide at different points. Now, it's not always true because the two surfaces are hard to kind of get to work correctly. But if I put the slick side on, right, and then I raise it up, right there it slid. So I'll do it again. There it slid. So you would do that a number of times and you would measure that angle. That's called the angle of repose or the static angle of friction. Okay. So it's friction's holding until you get to the right surface and then it goes. Now the sandpaper side should be much different. So when I go up with the sandpaper side, it should hold and slide at a much different point. And this one's on the metal, it's working pretty well. Here it slides kind of down there, maybe 30 degrees. And with the sticky side, I get up closer to 45 type of thing, right? So what's happening is when it's not moving, friction's holding. And when it lets go, you've hit that impending motion location, right? So graphically or statically with the forces, this is what's happening when we do that static angle. When we hit this angle of repose, since this weight is always acting vertically downward, these two are components of a resultant, which is here. So when it slides, that resultant is directly in line with the weight. This is called the resultant friction force. It's R. This is F. This is N. These are the components of R. Okay? So the tricky part is there is the static angle, and we use theta to denote the static angle. That's the angle that it slides. Okay, this is called the static angle of friction. So if we put R in, F and N go away. We literally can reduce one of the variables, right? We have two variables here, but if we put R in the diagram instead of F and N, then we can do something called a force triangle. We had P here. We would end up with three forces, 1, 2, 3. You can get this static angle from the relationship between F and N and R, and I know F equals mu S N. So they just give you the equation. They say, if you know the static angle, you can calculate that angle from the coefficient. It's tangent minus 1 of the coefficient. So the trick is, if you put R in there at its location, then you can use a force triangle instead of the simultaneous equations. And the force triangle will happen between the weight, the load, and R, not F and N, because we're going to remove F and N and put R in. So it gets pretty tricky because the triangle is not going to be a right triangle. It's going to be a non-right triangle. So we'll use this one where we had 175p and 25 degrees. I'm going to redraw it. So 175 P So this is kind of the second method where I'm going to put the axis in, Y and X, but I'm not going to put N, I'm not going to put F in. This one was impending motion down the hill, so I know F is here, but I'm not putting it in. I'm going to put R in. And what I do is I try not to put R vertically downward. I draw it on the side of this axis. F tells me which side to draw it on. If F was up here, I'd draw R up there, but it's not because we're doing impending motion downhill, right? And then this, it's always from N to R that is the static angle. And we get the static angle from this equation. We just take the inverse tangent of the coefficient. What was the coefficient on this one? 0.65, super sticky. So stay with me here because this angle becomes very important if you're going to go and make a force triangle between these three. So if you don't know that angle, then you can't build the force triangle. 25 degrees here, 25 here, 25 here. This is tangent minus 1, 0.65, 0.65, inverse tangent, 33 degrees. So you gotta be super careful because vertical downwards is gonna be the same as this, 25. Between N and vertical is 25. If between R and N is 33, then R can't be here. It's got to be greater than the 25. So if that's 25 and the static angle is 33, then R is out here somewhere. So R is this resultant friction force. If it's over here somewhere, then it's holding this block in place, and that's why P, we had to pull on it, right? If R was over here somewhere, then it's going to slide because it has no up the hill resistance. So you calculate the static angle from the coefficient, you get 33. You know the angle is 25 for the slope, so vertical to N is 25. Static angle from N, it's always from N, is R at 33. So it's got to be over here, not on this side of vertical. Once you get that, like once you've figured out, oh, where R is based on the slope and the static angle of friction, then you go for the forced triangle because you have 1, 2, 3, 1, 2, 3. So to get that forced triangle, I always start with P or some horizontal or vertical. That's fine. And it looks like it is going to create, because these two are 90, right? It's going to create a right triangle. So that's kind of nice. So you have to put these together. Oh, that's right. P's got to go the other way. The only way we can draw this forced triangle is if P goes that way. And then I got to put them together tip to tail. 175 goes down, so tip to tail, right? And then R goes up here. Whoops. R closes it. They're tricky to draw. So really what you want is these to be kind of in the same angular position. So graphically, I missed it a little bit. It does go up and to the right, up and to the right. P is probably just too big. So really P should be back in here, and then that angle looks the same. As long as you get the correct triangle built, it's not going to matter. You're going to put angles in and solve it. So downforce added to this one, this closes it. Should be in the same angular proximate position. So this does create a right triangle. That's nice. Not normal. Normally it does not create a right triangle. But once you get this, then you should be able to solve this thing as long as you can dig out an angle. The way I do it is I try to figure out R to vertical. So that is from R to vertical, not to N, because N's over here, some weird position, but R to vertical. And it's just the difference between the 25 and the 33, 25, 33. So 8 degrees, right? So from R to vertical is 8 degrees. Here is R to vertical, 8 degrees. With that, you have a right triangle. You should be able to solve it for P. So I know 175 is adjacent, so cosine 8 degrees equals 175. Oh, that's going to give me 175 over R. So maybe I want to use tangent. So I really want P. P is what I want. So what would tangent of 8 degrees equal? 175 over P. Ben's mind's been blown. It's too much partying in Texas. So then I solved for P. 175 divided by the tangent of 8 degrees. That didn't work. It's like some giant number. Oh, did I do bad? Opposite. Oh, yeah, these are opposite. Thank you. Opposite over adjacent. It was like getting 12,000 or something. That's definitely not right. So now what is it? Oh, it's a straight multiplication. You guys are supposed to catch me when I do stuff like that. I know I'm going fast though. 24.6 pounds. What do we get? 24.6 pounds. So it works. It's another method. There's no simultaneous equations, right? There is just a forced triangle, and actually this was a 90-degree triangle, so that was easy. This is hard. Like, to figure that part out takes a little bit of practice. What you do, though, is you just take F and N and get rid of it and put R in. You just have to figure out whether R is here or here, and it's all based on this coefficient. This arctangent of the coefficient to get that angle, and then you can determine where R is and go for a forced triangle. So there's definitely friction problems that require a forced triangle. Like, you'll just not be able to set up the equations with 2 variables. It just doesn't happen. All right, one more practice one, and then we'll be done. So I'm gonna do 35. If you have your book, you can look at it. If not, you can just look at this. It's 47 down. A weird 7. Come on, Ben, you can do this. Fight it, fight through it. I am. 35, that's it. It's a 47-pound weight, 29 pounds at 21 degrees. Again, just a bad angle for pulling. It's kind of an interesting problem because the problem says, is it going up? Is it going down? Or is it at rest? Like, it just basically is saying what is happening. Coefficient is slick, 0.15. I'll give you a second to draw that.
Is it nearly ice?
It's very close to ice. Here, I'm gonna Google it. What is
Or it
ice?
like ice? Probably so.
I haven't looked at ice in a long time.
Right?
47. It's number 35. If you have a book. Yeah, it's 47 down, 29 on the load, and 21 degrees and 33 degrees. Yeah, 0.15 is rubber on ice. Waxed ski on snow is 0.14. Wow. It's like the same. Rubber on ice and wax ski on snow. 0.14. Yeah, so this is 1.5. This is super slick. Right? It's just plain slippery. Like your tennis shoe on ice. But you don't weigh 47 pounds. All right, so we're going to set it up with the triangle method. So set my axis. I'm going to go X and X. And we have to like figure out where R is. So remember that R is from this normal location or the y-axis to R. And we can get that from this static angle. So it's tangent minus 1.15 is this static angle of friction. So we'll do that first. .53. And that is from R, whoops, to that y-axis. So from vertical to the y-axis is how far? From vertical to the y-axis is always going to be the 33. It's going to be your slope, right? And from R to N, or this y-axis, is only 8.53. So that puts R right in here somewhere. Huh? Yeah, that's our resultant for sure. So if I draw, so you can draw R to the left of that y-axis, or you can draw R to the right of the y-axis, because we're not sure which side it goes on, here or here. Right? Because I don't know if it's sliding down the hill, then F is here. If it's sliding up the hill, then F is here. Right? I just don't know which way it's going. So you just choose. Like, if I put it down here, then I'm assuming that F is here and it's potentially going down the hill. The other thing we could do is the equations to try and figure it out. So if we do it this way, we can do the force triangle to figure out R. Right? But let's see if I can draw that triangle. So if I know I got 47 coming down, and then I got 29 going up at 21 degrees. So I have to really try and keep this in perspective. 21 from here, 33. So it's like 54 degrees total. So there's 45. 54 is way up here. And only 29, it's like half. Right? And then R to close. So then I gotta figure out, like, how do I put this angle in? So this angle is to N, but if I had R to vertical is right there. So I need to get this one over here. So 33 is the whole way, 8.53 subtracted away from the 33, and we get that. $24.469. Definitely not a right triangle. No. So we need more angles because we have two sides, but we only have one angle. And that's not going to do it for us. We do know these two, right? We know the angle on the opposite side, so that's sine law. So we could use the sine law to try and solve this thing. Remember the sine law? 29 pounds over the sine of 24.469. And then I'd use the 47 pounds over the sine of, and I could get this angle.
How do you know exactly that 29 is?
How do I know the 29 is here? I don't know this angle. I know it's at 21 degrees, right? And I know that it's 33 is the slope. So like from here, from, let's see here, I can figure out that, oh, it's, if it was here, it would be 33 degrees, but it's another 21. So I went 54 from horizontal is where I went to get that 29. I try to just keep it graphically accurate. That's all you can do. But if I find this angle, then I can get this angle from interior angles, then I can go after R. Why do I want R? Because then I could go after F and N from R. And that would tell me like what's going on with the friction. But this tells me, because R is on the left side here, and I was able to make that, this is 24, so I was able to make this triangle. This tells me that the friction is down here. Okay, so let's go for this, which is just algebra. I get 42. So. I don't know if anyone else gets 42.
That's the go between 9 and R, right?
That's this. That's this. So that means I have this graphically drawn very bad. Right? It's not like this. It's which is all you can do is draw it that first time and then calculate stuff. But if this and this are going to be super small angle, then this has got to be like up in here somewhere. Right? So there's the 29. Here's the 47. Here's R. And here is a more appropriate 42 degrees. So that's telling you that R is not on this side. R is definitely up in here somewhere. Because of that angle, this big angle. So if that's the case, then F has to be here because this is being, these two combine to get that. So that means if F is here, impending motion is definitely up the hill. So up the hill is what's going on. So that's kind of a rough way of coming up with it, but that's how you do it, forced triangle method. So on this one, equations might have been easier because then you just run the equation, you make a guess as to F, you run the equations, and if it comes out negative, you know F is going the other way. If it comes out positive, you know F is good. Forced triangle method, you just figure out where R is, put it in, and know F opposes motion. So tricky. All right, yours are not as tricky, but I think I did give you a ladder problem. So because you can't do friction without a ladder problem. So I gave you 41, which has a bunch of information. And really what happens here is if do they give you coefficient? Oh, they give you mass. So you're going to work it in metric. And they give you a coefficient of friction on the wall as 0.2. And they want you to calculate the coefficient of friction of the floor. So what you're going to do is you're going to go here, here, and here, and here. Right? So you're going to have a lot of unknowns. 4 of them. This we know as a weight, and we know its location. So what you're going to want to do is you're going to want to put in R here, and you're going to want to put in R here. And what you don't know is that. That you don't know, but you do know this because you know the coefficient here. So you're going to end up with a forced triangle that looks something like this. But this one, you'll know where it's at. This one, you know the weight. This one, you're not going to know the angle, but you're going to want to find out the angle. So forced triangle is definitely the way to do this problem. Don't go for equations. You're going to be really challenging with equations. So try this. Try to put R in, get rid of F and N. You'll know the angle because you know the coefficient for the wall. It's 0.2. You will not know the angle down here, but we know R goes here because we know F is going to resist the ladder or else the ladder is going to fall. So you should be able to build that forced triangle between R and the weight. And then we'll clean that up on Wednesday. So good luck with that. And we'll be done with friction.